Hey, I want to very briefly show you something called Pascal's triangle, which will help us do some algebraic computations very quickly that otherwise would be tedious. Pascal's triangle is a triangle of numbers, and it starts with two ones at the top. And then each row after that starts and ends with a 1, and in the middle we get a number that we find by adding the two numbers above it. So in other words, that 2 that you see there comes from 1 plus 1, and that's what gives us the 2. Which makes the third row 1, 3, 3, 1, because 1 plus 2 is 3 and 2 plus 1 is 3. And the next row 1, 4, 6, 4, 1. And again, the 4 here comes from 1 plus 3, and the 6 here comes from 3 plus 3. And I'll do one more. The next row is 1, 5, 10, 10, 5, 1 for the same reasons. So take a moment, make sure you understand the pattern, and then see if you can write down what the sixth row of Pascal's triangle is. So pause the video if you need to, write down the sixth row of Pascal's triangle, and we'll see if you really get it. And you should have come up with 1, 6, 15, 20, 15, 6, 1, where the 6 comes from 1 plus 5, and the 15 comes from 5 plus 10, and the 20 comes from 10 plus 10, etc. Pascal's triangle has all sorts of very interesting properties that we will not be looking at. We're going to be looking at it, how we use it practically to do some algebraic computations. And for example, here's one that you already know. Suppose you were computing x plus 1 squared, which is x plus 1 times x plus 1. You do the work, you distribute, you get x squared plus 2x plus 1, or 1x squared plus 2x plus 1. And the 1, 2, 1 that we have as the coefficients there are the 1, 2, 1 from this second row of Pascal's triangle. Pascal's triangle, often called Pascal's triangle of binomial coefficients. It gives us these coefficients, the 1, 2, and the 1. That was just a specific example of one that's very accessible that you've seen before. But more generally, suppose we wanted to compute a plus b to the fourth, whatever a and b are. Well, we'd look at the fourth row of Pascal's triangle. That's where the coefficients will come from. And the first term will be 1 times a to the fourth. And the next term will be 4 times a cubed b to the first, plus 6a squared b squared, plus 4ab cubed, plus 1b to the fourth. Where the 1, 4, 6, 4, 1 came from the fourth row of Pascal's triangle, and then we started with the powers of a and b, the powers of a decreasing from 4 to 0, while the powers of b increased from 0 to 4. So in that first term, we had 1, a to the fourth, b to the 0, if you like. And then the powers of a went from a to the fourth to a to the third, a squared, a to the first, and then a is not there at all. You can think of that as a to the 0. While on the other hand, the powers of b ramped up from 0 to 4. And you say to yourself, that's not so interesting. But what if you needed to compute x plus 3 to the fourth? Well, one way to do it, of course, is to write x plus 3 times x plus 3 times x plus 3 times x plus 3 and do all the work and distribute each time and come up with some fourth degree polynomial, but that's a lot of work. Another way is to use Pascal's triangle, which basically just gives us the answer. It's 1 times x to the fourth, and then the next coefficient is a 4 times x cubed, and then that second term raised to the first, so that's 3 to the first. And then the next coefficient is a 6, and the power of x goes down and the power of 3 goes up, so it's 6x squared times 3 squared. And then the next coefficient is a 4, and the power of x goes down yet again, so it's 4x, and the power of 3 goes up, so it's 3 cubed. And then finally 1 times 3 to the fourth. And then all that's left is to do a little simplifying, and you get this expression here, where the hardest part is probably doing the arithmetic of 4 times 27 to get the 108. Other than that, and not that that's so hard, you get this expression here when you're all done. And so certainly that was a lot easier than taking x plus 3 and multiplying it by itself 4 times. And this will come in quite useful in some of the things that we do in upcoming lessons in this class. Okay, you try one. See if you can compute x minus 2 cubed using the third row of Pascal's triangle. You know, when we did x plus 3 to the fourth, we used the fourth row of Pascal's triangle because it was to the fourth power. Since this is to the third power, use the third row of Pascal's triangle. Take a moment, pause the video, see if you can come up with the answer. And when you pull the coefficients out of the first row and you make the powers of x decrease and the powers of -2 increase, you get this expression here, 1x cubed plus 3x squared times -2 to the first, plus 3x times -2 squared plus 1 times -2 cubed. And all that's left is to simplify. And if you're careful with your signs, you end up with x cubed minus 6x squared plus 12x minus 8. That's it. There's lots more to know about Pascal's triangle, but that's all we'll be using it for some practical computational reasons. It's worth mentioning that it shows up on things like the GREs sometimes, not explicitly, but they'll ask you something like, what is x plus 5 to the 7th, or something like that. And what they really want is they're hoping that you'll be foolish and take x plus 5 and multiply it by itself 7 times, and maybe you'll get the right answer if you don't make a mistake, but you'll just have used up 20 minutes of your time in their timed tests. But if you know this trick, then you can figure out x plus 5 to the 7th pretty darn quickly using Pascal's triangle, or at least enough terms of it to choose the right answer out of a multiple choice question. So a good trick to have up your sleeve for standardized tests, and something that we will be using in a couple of the upcoming lessons. See you soon.